All right. So now let's put this situation into motion. Okay, we want to actually put our situation into motion. And we want to start describing some things that we can see. Well, first of all, we'll draw our situation here. I've got my spring. And what will happen is if this is at rest, we can represent this as a 0 point when the system is at rest. Now what's going to happen is we're going to disturb the system. I'm going to pull it down a little bit. And if I pull it down a little bit, it's going to go here. And without friction, this distance here and the distance above that equilibrium point, those two distances are going to be the same. Okay, those two distances are going to be the same. We're going to call that A. And A is going to represent the amplitude of my system. That's how far it's going to go up, and it's how far it's going to come down. So we can actually have this as A, and we can have that as A. So the position at any time that we're looking at this, our position at any time, I want to make sure I'm not messing anything up. What's going to happen is if I were to put a marker on this, I'm going to get, and as this bobs up and down, and if I were using a piece of paper and pulling it around, I didn't draw it very well, so I can actually, you can actually see what's happening here. I'm going to get something that's going to look like a sine wave or a cosine wave. Now remember, a sine wave and a cosine wave look exactly the same, except for one big difference. If I do this, if I look at the sine of some value plus 90 degrees, that's going to equal the cosine of some value. This we'll refer to as what we call a phase angle. And all that phase angle is going to do, it's going to tell you where you are when t is equal to 0. Right? Just going to tell you where you are in your curve as t is equal to 0. So what we're going to do is we're going to use a mathematical model. And we're going to use that sine and cosine wave, and we're going to choose to use the cosine. There's a reason why we choose to use the cosine, but you could have just as easily used the sine and did this, but there's a reason why we choose the cosine, because it's going to do our positives and negatives a little bit better. But we're going to be able to bob our system up and down. We're going to be able to generate that kind of a sine wave going back and forth. And we're going to use the cosine. So we're going to say that the position of this ball at any time, and I can use y or x because I'm in linear motion, and we like to use x instead of y, even though I'm up and down. I can say that x is going to equal some a cosine, and I'm going to put something in there to represent my position. Now, we've got it moving, so this has got to be a function of time. And that function of time means I'm going to put in my time value in here. Now, this is where things get fun, okay? First of all, let's look at my cosine and my sine. Sine of any angle is going to have a value between +1 and -1. Cosine of any angle is going to have a value of +1, -1. So as I'm going around with this cosine here, the maximum value that cosine can have is 1, and the minimum value can have is -1. Well, that's going to describe my motion here. The maximum value is going to be A, my minimum value is going to be -A. If I do it on this kind of a document, my maximum value is here, my minimum value is here. My wave peak is up here, my trough is down there. And we're following this in terms of time. So let's look at my other model. One of the other models is the unit circle model. And as my object goes around this circle, the time that it takes to make one complete circuit, or one time completely around the circle, we refer to that as T, or the period. All right, and that's going to be in seconds. Now, the distance that my bead has traveled around the circle, if I am thinking about this angle here, that's going to be 2 pi. All right, 2 pi around my circle. And remember that period is equal to 1 over frequency, or frequency is equal to 1 over the period. So 2 pi times the frequency is going to give me our angular velocity. Or it's going to describe how fast my object is going above the circle. Now, what's interesting about this is if I look at this situation head on, if I'm looking at the x direction, I'm going to get my sinusoidal pattern just like that. If I'm looking at my y direction, I'm going to get my sinusoidal pattern just like that. And I've got it going both directions. So this is great. So what's going to happen here is I can put that omega right here. And now for this system, I can describe my position above or below this equilibrium at any time by looking at the amplitude and looking at my angular frequency. So I can describe that position. I can do the same thing here. I can describe my x position or my y position. I'm just looking at it in one dimension. And we can look at our other system, the other system that we've been talking about, my pendulum system. And again, if I had a marker as this swings back and forth, I'm going to get that same sinusoidal pattern that I got before. So what we've done is we've created a mathematical model to be able to describe the motion of that system, the motion of this system, the motion of that system. And we now can tell you the position at any time as it's moving back and forth around its equilibrium point, or if we're moving around our circle, or if we're bouncing up and down, by using this equation of motion. So I can plot this. I can take a graph. I can take a graph that looks just like this. All right. And I've got a plot here. And we're going to say that this is T is equal to 0. And I can tell you, and I can actually have, say this is 5 and this is 5. If I've drawn this pattern, I can read right off the graph that the amplitude is equal to 5. And at t is equal to 0, so if a is equal to, or I've got a is equal to 5, I have x is equal to a cosine omega t, all right? And I've got t is equal to 0, and x is equal to 0, so I've got 0 is equal to a cosine of 0. I can figure out what my phase angle is, or I can read my angular frequency. I can do this. I can read my angular frequency because this time, so let's say that this is 5 seconds. That's the time. So the period I can read right off of here is 5 seconds, which means that 2 pi times the frequency is going to equal omega. And frequency is 1/5, so this is going to be 2 pi divided by 5. That's equal to omega. And I can make that a more general one and say that x is equal to a cosine omega t plus phi. And I can go in and figure out what this phase angle is, because I know that at 0, this plus my phase angle has to be 0. So cosine of some value has to equal 0. So my phi is going to be the arc cosine of 0. If I did that. And the cosine of 0 is equal to 1. I'm sorry. The cosine of 0 is equal to 1. So that's going to be 90 degrees if I do the arc cosine. That's going to be 90 degrees, or pi over 2 if I want to stay in radians. So you can take a graph of your system and be able to just read your components. So that's going to make life very helpful. Now, remember, we're doing motion here. So our x is going to be a cosine omega t plus my phase angle. My velocity is going to be minus a omega sine omega t plus the phase angle. And my acceleration is going to be minus a omega squared cosine omega t plus my phase angle. So if I want to go ahead and look at those things, I want to be able to go back and forth. Now remember that omega is equal to 2 pi times f, and this will give you equations 13.14a, 13.14b, and 13.14c. So you will actually see these in your text. We can go back and look at my forces. So I can have force is equal to mass times acceleration, which is equal to minus k times my x. And my acceleration is going to be minus k over m times x. And I want to show you that k over m again is giving us our spring constant, and our mass is starting to give us that description of how we can build our models to emulate a lot of different things, so that you can look at those pieces. So that really makes it helpful for how you're looking at the description. So I could give you a problem that looks like this. I'm going to give you a system that is modeled using the following equation. X is going to equal 0.5 meters cosine pi over 2t, and that's my system. I can ask you, what's the amplitude? Well, remember, this is modeled by a cosine omega t. All right, so my amplitude I can read right from my equation. That's going to be 0.5 meters. My angular frequency is going to be pi over 2. But I can calculate this frequency, because remember, omega is equal to 2 pi frequency. So omega divided by 2 pi is going to equal the frequency, which means that I get pi over 2 divided by 2 pi. So I'm going to have 1/4. I can get to the period because the period is 1 over the frequency. All right. Well, 1 over 1/4, the period is going to be 4 seconds. I can also tell you now what's the velocity. Well, the velocity is going to be that right there, so I can plug in my numbers to give you velocity. So velocity is going to equal minus 0.5. My omega was pi over 2 sine pi over 2 t. That's my velocity. I can take it the next step and I can put in my acceleration. And I can get you that. And we've already been able to represent and look at our wave functions to be able to represent those particular objects. Question.